Welcome to the National Instruments Analog Video Test Application Demonstration. Over the next few minutes, you'll see how a National Instruments high-speed arbitrary waveform generator, a high-speed digitizer card, and powerful software such as TestStand can be used to perform analog video measurements. We will also be using a product from one of National Instruments' Select Alliance members. This product, VideoMaster from Microlex, is a comprehensive library of tests for composite, S-video, and component video formats. There are many formats of analog video signals. For this demonstration, we'll be concentrating on composite video signals. In this type of video, three components, the luminance or brightness of a signal, the chrominance or the color information, and the synchronization signals are all contained in a single channel. There's a slight variation of composite called S-video, where the luminance and chrominance information are split into two separate channels to improve the quality of the final video. However, most of the same tests that we do for composite video still apply. There are also several standards defined for composite video signals that define the number of lines, the vertical resolution, the frame rate, and other characteristics. The most common standards are NTSC, PAL, and SECAM. These standards are for the most part regional. For example, NTSC is the primary standard for North America, and PAL is used throughout most of Europe. Now let's take a look at the basics of a composite video signal. First, the luminance and synchronization information. The synchronization information embedded in a composite signal tells us the beginning of a new frame of an image as well as the start of each video line. Here we see the horizontal sync pulse determining the start of a single line of video, with the luminance information imparted as the amplitude of the waveform. White is the largest values allowed for the amplitude, and black is at the lowest level. The color information, or chrominance, is then encoded into a video signal using a special subcarrier frequency. A reference signal is contained at the beginning of each line of video, with the color packets modulated on top of the luminance signal. The phase of color packet contains the color or hue, with the amplitude of the packet giving us saturation. When testing a video signal, the first thing to consider is the measurements that you want to make to qualify your unit under test. There are a variety of tests for composite video signals, some dealing with the time domain and others dealing with the frequency and phase information contained in the waveform. For each measurement, there must be a video pattern that is generated by or through the unit under test that contains the characteristics we are interested in. For example, in this slide, we are testing a video switch, so we need to generate a video pattern that contains all the elements that we're interested in that applies to the video measurements we're going to make. In this case, the signal that we are generating is a color bars pattern. So on the screen, you would see a series of bars representing different colors starting at white and going all the way through black. This pattern would be passed through the unit under test, in this case a video switch, and on the other end we would acquire the signal. Here we see the full composite video signal with the horizontal sync pulse, the color burst, and then the representation of each of those color bars. Now let's go on to the demonstration. For this demo, I'll be using two modular instruments from National Instruments. The PXI 5421 is a 100 megasample per second arbitrary waveform generator, and the PXI 5122 is a 100 megasample per second 14-bit digitizer. I'll be using the TestStand product from National Instruments with VideoMaster from Microlex. Now let's take a look at TestStand. TestStand is a ready-to-run test management environment for automating test and validation systems. I've already started a sequence to automate the test that I want to run on my video switch. The first step is written in LabVIEW and communicates with the 5421 arbitrary waveform generator to generate the color bars pattern. The 5421 has up to 512 megabytes of onboard memory. This instrument allows me to define the long, precise waveforms necessary for testing video. Once it's generated, it's passed through my video switch, and then I'm going to create two tests that acquire the signal through my high-speed digitizer and actually perform the measurements. For this, I'm using a configurable TestStand step type that is part of the VideoMaster product from Microlex. VideoMaster is written in LabVIEW, but the configurable TestStand step type allows me to configure my acquisition and my measurements from this front panel. So I set up my acquisition to be a composite video signal with the NTSC standard. I choose a full frame of video, I configure it, initialize it, and acquire a waveform all from this front panel. Once I acquire the waveform, you can see what a single line of video is here on the front panel. You see my horizontal sync pulse, my color burst, and each of the color bars represented on this front panel. Once I've acquired the waveform, I can actually make the measurements. VideoMaster has a comprehensive set of measurements for composite video, but with this particular pattern, there's two tests that I'm interested in. First, horizontal timing. I'm going to use this line of video to check out my sync pulse, my burst that has my reference signal for my color information, and my blanking interval before and after my active video. Here you can see the measurement results to the right. Besides horizontal timing, I'm also going to create a step that measures the color bars specifically. Here I get back my luminance and chrominance information divided up by the different color bars that were in my generated pattern. From the luminance, I get my amplitude information, and from my chrominance, I get the amplitude of each color packet along with the phase information. With these tests defined and created, I can then go back to the test stand product and create limits. In automating my test, I'm going to want to define what constitutes a pass or a fail. Test stand allows me to easily define for each of the information passed back from a configurable test stand step type what is acceptable and what is not. Once I've configured my limits and my sequence, I can now run the sequence on a series of unit under tests. Test stand asks me for my unit under test information to identify each unit, and then runs each of the test steps on each unit. Once I'm finished, I can take a look at my results in an automatically generated report that shows me all the results and whether it passed or failed for each of the units I've tested. That concludes the demonstration. For more information, you can go to the World Wide Web and take a look at the modular instruments pages at www.ni.com. You can take a look at the VideoMaster product at Microlex's homepage. Thank you for your time, and I hope you've enjoyed the analog video testing application demonstration.